says find the exponential function f of x equals b to the x, whose graph is shown below. Okay, so remember, any function of the form f of x equals b to the x is the parent function. So this is your parent exponential function, your basic graph. Okay? Anytime you have a function of this form, notice there's a 1 right here in front. We don't bother to put it in. There's a 1 multiplying the x. Every single exponential function that has this form will have the following y-intercept, 0, 1. Always. So when you look at a graph, you see 0, 1 as the y-intercept. You know it's going to have this form in the x. You know something else from looking at this. You know something about the value of b. Remember, this came with 2 flavors, vanilla and chocolate, right? With 2 flavors. There was exponential growth. And for exponential growth, we said our base, our number b always had to be greater than 1. When we had exponential decay, we knew that our base b has to be between 0 and 1. Am I recording? Let's see. I am recording. Yes. Oh, I don't have my ears. So I guess I'm not recording. Okay. Yeah, I'm recording. All right. Thank you. So when we look at this graph, which of these 2 flavors is it? Is it growth or decay? It's growth. Because as we move from left to right, this curve is starting to grow pretty quickly, increase pretty quickly. So we know something about the value of b. B has to be a number bigger than 2. So now you say, how do I find the value for b? The value of b. Well, it's always given to you if you can determine the point 1 comma question mark. Because 1 comma question mark is always the y value when x is 1 is always your value for b. So in this particular case, it's 1 comma 5. That automatically tells you that b is 5. So you're all done. You don't have to do any other work. There you are. There's your exponential function. Now, suppose you didn't know that. Suppose I hadn't told you that, and you wanted to try to figure out how to find b. Well, just like when we have a line and we know a slope, or we have a quadratic and we know the vertex and we're trying to solve for the leading coefficient, or we have a polynomial and we know all our zeros and we're trying to find the value for a, if you know 1 point on your graph, that's going to be an x value and it's going to be the f of x value, and that will always help you to solve for your unknown. So let's suppose we didn't know what b is. You take any point where you can definitely know the coordinates, and it doesn't matter which point you choose here. But this is a key point. So let me show you why you can always feel comfortable just saying, hey, if I can find the y coordinate when x is 1, that's my base. Because if I fill in now, x is 1, f of 1 equals b to the 1. And what is f of 1? F of 1 is the number 5. So 5 equals b to the 1. Well, b to the 1 is b. So I'm all done. I know what b is. So I have my function, 5 to the x. You're all done. There's no other work to do. If you are a little in doubt and you don't trust yourself, plug in this point. This says when x is 2, my output, or the value of my function, is 25. So come down here. 5 squared is 25, and you're very happy. Okay, so that's all you have to do. So what I'd like you to do now is I'd like you to turn to today's activity and do number 1 at your seats. Okay, so what did we get for this? For the value, what function can we illustrate by the first graph? F of x equals 10 to the power of x, right? Because when you know the value of your function for 1, that becomes your value for b. Okay, so let's move along. Let's go back now to number 10. So your quiz on Friday will be on classes 28 through 32. And now remember, this set of lecture notes is 32 and 33. So it goes right up to this problem right here. This is where we stop for the quiz. Everything else after this will not be on the quiz. So we stop right here from 28. 28 was long division of polynomials. 29 was all your zeros. 30, 31 was rational functions. And up to this point is where you stop for your quiz. Okay, any questions on that? And don't forget, you can always bring in an index cards with notes, right? So having the steps for graphing your rational functions wouldn't probably be a bad thing to put on your cheat sheets, right? All right. Huh? No, but you can have both sides, and they're on my door. Okay, so now, folks, it's really hard when I know some of you are excited and you're doing the activity on your own, but if you could just, the little chatter is kind of hard for me to talk over, so I appreciate it. If you just kind of do it quietly at your seats. If you're moving ahead, that's fine. So here I'm telling you that both of these graphs represent transformations of some basic graph b to the x. We don't know the value for b yet. So they're going to be transformed, and you have to determine, have I moved them horizontally? Have I moved them up and down the y-axis? Have I stretched them or shrunk them in any way? Those are our transformations. So remember, one of your key points is the y-intercept. We know that on regular old b to the x, our y-intercept is 0, 1. We know that that's true on our regular old y equals b to the x. Whatever b is, it's going to go through 0, 1. So, and I don't know really where the rest of this curve goes. I'm just going to do this like this. So this could be b to the x. So if I compare my red graph to my black graph, and I ask you, not even for the details, but what type of transformation has occurred here, what would you say? Don't tell me like the particulars, like the number or anything, but what's happened to the red graph to make the black graph? It's shifted up, right? The shape is exactly the same. You've just shifted it up. So you know that this function, our new function g of x here, is going to look like b to the x plus some constant. Okay? So now you've got to figure out, which constant is it? Well, compare that key point, your y-intercept. What's the y-intercept on your black graph? 0, 4. So how far did that point move? Be careful, from 0, 1 to 0, 4, 3, right? So g of x is b to the x plus 4. We've got half of our work done already. Oh, 3. We just, I know. Wait a minute. Right. But I just told you, Brittany, it wasn't 4, right? And then I put the 4 in. All right. Now what do? How do I find b for my black graph? How do I find the value b? What point do I go to? My x equals 1 point. Let's take a look at that. Here's x equals 1. I'm going to go draw a straight line right through 1. Oh, good. It actually hits it at a point where I can see what the coordinates are. So does that automatically mean that b is 5 now? No, because that's only true when I start off with my parent function. But I can use that point, put it into my equation here, and I can solve for b. So I use the point 1, 5 to solve for b. And once I do that, I am home. Okay, so let's see. When x is 1, the value of my function is 5. So there's a linear equation to solve. 5 equals b plus 3. 5 equals b plus 3. So what's the value of b? 2. So the value of my the graph here, that's this black graph, is 2 to the x plus 3. So g of x here is 2 to the x plus 3, because I have a vertical shift up of my parent function 2 to the x. So here's f of x equals 2 to the x. Okay. So That's all that's happening there. Okay, so this is why we spend so much time on transformations, because we use them over and over and over again. Here's another little idea for you to consider. Anytime you see the horizontal asymptote, notice on our original parent function, the horizontal asymptote is 0, the x-axis, as x gets smaller and smaller and smaller as it goes towards negative infinity. If this was some kind of stretch or shrink, then that asymptote wouldn't have changed at all. It would still be right above the x-axis. So literally now you can see that the asymptote is no longer y equals 0, but y equals 3. There it is. There's your asymptote right there, your horizontal asymptote. So again, that's one way. When you see the whole thing has been moved, including the asymptote, you know it's a vertical shift up. Versus the next one. Have I vertically shifted that up? No, because notice you have the same horizontal asymptote out here. But what's happened is it's rising a lot quicker. Look, at 0, instead of being at 1, it's at 3. Okay, so this is being stretched, right? So find a couple of points. 0, 3. We find any other points on here that we can very nicely label with the coordinates? 1, 6. And that's really all you need here, folks. Okay, so this looks like h of x equals some number is going to be multiplying b to the x now, because I have a vertical stretch going on here. So that's going to be a number out front. So how do I find that number? Well, when it's our regular old parent function, it's always a 1 out front, because that's my y-intercept. So what's your guess to the value of a here? Do you have a guess? 3, right, but let's verify it. When I put 0 in for x, my output is 3. So my output is 3 when I put 0 in for x. Well, b to the 0 is 1, so 3 equals a. So I've got part of my function already determined from looking at that y-intercept. That's the number that goes right out in front here, 3. So that's where I put my 3. It's my vertical stretch by a factor of 3. Now, what the heck is my base? Well, I use the 0.16, use this point to solve for b. We've got the a value part figured out, so let's figure this out. H of x equals 3b to the x. So this tells me that the value of my function is 6 when x is 1. So 6 equals 3b. So what's b equal to? 2. So this black function here is a vertical stretch by a factor of 3 of my basic function 2 to the x. And that's how you figure it out. So basically, you're just using the points on your exponential function to give you the value of a, if there's a value of a other than 1 out front, and the value of your base. You just plug them in. Okay? Any questions on either of these two? I said use this point to solve for b. Use this point to solve for b. Okay. Just like over here on this one, Jonah, we used 1, 5 to solve for b over here. Okay, so at the end of class today, you're going to have lots of times to name that exponential function, but we're not doing this right now. We're going to continue along. And you're also going to have a chance to match some functions. But before we do that, now I did not include on your homework that's due Friday problems that involve interest. But so on your own, obviously you won't be graded for it because it's not on my math lab, but for practice, go to section 4.1 in your textbook and look for problems involving interest. And I think it starts with number 53, like 53, 55, 57. While you're all working, I'll check it out online and I'll give you specific problems, okay? You do not have these in your notes, in your lecture notes, so unfortunately you have to be like life used to be in any old math class. You have to take notes for like the next 10 minutes. So if you don't have any paper, I have some scrap paper up here. from the studio. If you need a piece of paper, let me know. Anybody need paper? So unfortunately, you know, I'm just going to spread this around. Take it if you need it. Okay. I know it's going to seem like going back to the dark ages to take notes in math class, but that's what we're doing. Okay. And we're going to start with a fictitious problem because there's no bank account that I know of that will give us an interest rate of 10% a year. But I want to just go over some terminology with you. Whatever hunk of money you invest, whether it's in a bank, a stock, a mutual fund, a bond, is called your principal. So in this particular problem, our principal is $100. It's not a lot, but hey, it's something. So we got $100 and it's called the principal. We use the letter P to denote it. Okay, so P is our principal. We use the letter P. Now, when you put money into a bank account, your money works for you. Not as hard as we'd like it to work, because our interest rate, the interest rate that the bank pays, or the rate on giving them the privilege of using our money to then go off and loan money to other people at much higher rates than what you're getting for investing it, is how banks make their money. Okay, so this particular bank's going to give you 10% a year. This is called R. This is called your interest rate, R. Okay, so if we're just looking at 1 year now, just how much money would we earn at the end of 1 year if I put $100 in for 1 year at this percentage, at this rate? Well, a lot will depend on how many times the bank compounds it. Well, the simplest way to look at this, to understand these formulas you're about to see, is suppose the bank just says, you're going to have that $100 in there for an entire year at 10%, and at the very end of the year, I'll give you 10% on your investment, and we'll add that to your amount of money. So let's say A of t, we're going to write a function. The A of t is the amount of money that I've accumulated in the bank after 1 year. So this is the amount of money in dollars that I've accumulated at the end of 1 year. All right. So does anybody know how I would actually find A of 1, how much money I would have after 1 year? So how much money would I have after 1 year? What would I do? Yep, Cooper? My principal. So let's put a general formula here first. A of t is my principal. Yeah, and then well, yeah, there's shortcuts, but do you all see that I'm going to start off with, for 1 year, here, I'm going to have $100. And then I'm going to add to that my little bit of principal I earn. And how do I find, my little bit of interest? I take my interest rate, 10%. Well, the first thing I have to do is change 10% to a number, which is the decimal 0.10 or 0.1. And I multiply that times my principal. Okay, there it is. So I have $100 plus this little extra money the bank's going to give me. And the bank's going to give me 10% of $100, which is how much? 10. So this is 100 plus 10. So at the end of the year, at the end of 1 year, hey, look at that. I got 10 extra dollars for putting the money in the bank. All right. In general, if you look at this, let's go back to our general formula. If I asked you to factor this expression, P plus PR, how would you factor it? It's on the palms of your hand. Greatest common friend. What's the greatest common factor there? P. So if you pull a P out, what's left? You've got to have two things in here. 1 plus R. Right. So as Chris said, wouldn't it just be 100 times 1.1? Exactly, because if I follow this recipe, 100 times 1 plus 0.10 That's 100 times 1.10, which is $110. Okay. So we're going to be working with this formula for a couple of times today, a couple of times here, and see what happens. So now I found a bank that's going to take that $100 and they're going to compound my interest twice a year. Okay, so what that means is instead of applying the 10% just one time at the end of the year, we're going to apply it twice. So that means they're going to divide the 10% by 2. And they're going to apply it after the first 6 months and then again at the end of the next 6-month period. So the first thing they're going to do is they're going to take that 10%. So my rate now, so semi-annually means it's going to happen twice. That's what semi means, twice a year. And I'm going to get 0.05 for my interest rate. Okay, so 5% interest twice a year. So that means it's my $100 times 1.05. So this is how much money I get at the end of my first 6 months. So this is how much I earn at the end of my first 6 months. So how much is that? 100 times 1.05. $105. I know, huh? I know. I'd love to have this bank. All right. So at the end of the next 6 months, we're going to earn 5% on this. So now I take the amount of money I have, 105, and I multiply it by 5%. 5% is all of the amount, 100% plus 5%. That's where the 1.05 comes from. The entire amount, 100% of 105 plus 5% more. And that's going to give me a grand total of $110 plus 0.25. So you can see here, if I started off with my original amount, I did 1.05 times 1.05. That's how I got $110.25. So it now looks like this, 100 times 1.05 squared. Okay, let's look at where each one of these numbers came from. The 1.05 we got by adding 0.10 divided by 2 to 1. And I had 2 compounding periods, so I put a 2 up there. So let's think about compounding it 4 times a year. Let's see if we can just use this little formula here. So the amount of money I would have after compounding it 4 times a year is my principal, 100. 1 plus, I'm going to take that 10% and divide it up into 4 equal parts, 0.10 divided by 4. And I'm going to do this every 3 months. I'm going to do it 4 times during the year. So this would be 100 times 1.025 raised to the 4. How much more money do you think we're going to get? Anybody have a sense? We do it 4 times? Huh? You don't know. Any guesses? Doesn't matter. Doesn't hurt to guess. Oh, so you think we only go up like 50 cents or something? All right, well, let's try it. I'm going to let my calculator do some of the work for me. So what's my formula starting to look like? 100 times 1 plus my interest rate, 10% divided by the number of times I'm compounding. So that's going to be my variable. So let's clear everything out of here, out of my calculator. Whoops, how come nothing's happening? My calculator's not working. That's weird. Exit without saving state. Let's try it again. What would I do without my calculator? Let's see. Clear. Oh. Wow. Don't reset calculator. How's that? Let's try that. Oh, RAM cleared. Okay, everything's out of there. Y equals. All right, Y equals. So I'm going to put 100 times 1 plus my interest rate divided by the number of compounding periods I have. That's our variable. And the whole thing's raised to the number of compounding periods because I'm just doing this for 1 year. So let's see what this expression equals when I do it once a year. So X is 1, twice a year, 4 times a year. So I'm going to go to set my window. I start at 1. And I don't want it to do it automatically. I'm going to tell it how many compounding periods I have. So let's go to my table. And once a year, there's my 110 bucks. That's what we found back here, 110 bucks right here. Twice a year, we should get 110.25. Let the calculator do the work. There we go, 110.25. 4 times a year, this is the big mystery. Let's see, 4 times a year. Oh, great, 13 extra cents. Still money, you're right. All right, so I get $110.38. All right, now it's gotta really start to grow, because look, I'm gonna do it every single day. So I'm gonna divide 0.10 by 365, and even though that's a really small number, I'm raising it to the 365 power. So write down a guess how much money you think it will be, just at your table, nobody's gonna look. If I do it every single day for a whole year, I'm gonna put in 365. Write down your guess, nobody's gonna see it. How much money? It's gotta be bigger than $110.38. Just write something down. Ready? I'm gonna hit the enter button so you can see how close you are. Here we go. Whoa, 52 cents. Oh my God. Look at that. Another 14 cents we earned. All right, well, now I'm going to get ridiculous. We're going to compound it every second of the year. And how do you figure out how many seconds are in a year?
That song from Brent.
Yeah, that's nine. That's minutes, though, is it? 900, da 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 da, 600. Yeah, the song for rent. Right. Well, all right. So that's a round off that song by Rent. If you take chemistry, you're going to love this thing called dimensional analysis, because it's how you get through any science class. There's 60 seconds in every minute. I don't want seconds per minute. I want seconds per year. So now I got to do, stoichiometry, 60 minutes to every hour. No. Notice here's your foo-foo, minutes over minutes. Now I get seconds. I got 3,600 seconds in 1 hour. I don't want hours, so I change my hours to the next bigger unit, day. Foo-foo. And then 365 days in every year. Okay, now all my foo-foos are gone. The only unit I have in the top is seconds. I've got 30 times 24 times 365 seconds over 1 year. So let's see what number that is. It's pretty big. Let's see. Let's go back to, okay, 30. Oh, but it should be 60. What am I doing there with 30? Yeah, come on. What's with that anyway? 60, I looked at the last number. 60 times 60 times 24 times 365. Whoa, baby. 3153600. So these are how many seconds you have in every year. So don't waste a second. And and always spend your life in math class, because it will last longer. No, I didn't mean that. All right, so let's say this is the number of times I compound. I'm going to do it 31,536,000 times. So let's go to our table and do it. Let's write that in for X. 31,536,000. So now write your guess for how much money I'm going to have after I do this 31 million times. Write it down. Don't say it out loud. See how close you get. The closest person, well, I can't do this because some of you are already doing it on your calculator. All right, ready? See how close. Enter. It didn't even change. You know where it changes? Out in like the third or fourth decimal place, so it rounds it off to the same. So the moral of the story is, the more you compound, it does make a difference, but after a certain point, it's really a small amount of money, at least when you're dealing with hundreds of dollars. I mean, if you're out dealing with millions, it's significant, right? So we're reaching a limit here, folks. We're reaching a limit. We're reaching a horizontal asymptote. Whoa, let's look. Here's what we just graphed. We graphed y equals 100 times 1 plus 0.10 over x to the x power. This is going to start at 100 bucks, and it's going to grow. but it's not going to grow forever and ever. So let's set our window and take a peek at it. Our window starts at, well, we'll start at 0, even though we'll get an error there. We're not looking at the value anyway. X maximum, well, we don't want to go out to like 551, trillion, quadrillion, gazillions. So let's just say X goes to 50. X max is 50. What's our Y minimum? Y minimum value is how much money we have is $100. And it looks like 111 might be good enough. So let's put 120 for our maximum and see what this graph looks like. It's growing very, very slowly. It almost, see, it's growing, but it's reaching a horizontal asymptote. What is that horizontal asymptote? The horizontal asymptote that it reaches involves this thing. An irrational number that's so special we give it a letter for its name. It's called E. E, little baby E. Euler is the guy's name. Go back in history. But anyway, it's an irrational number, which means you can't represent it as a fraction. There's no fraction that will give you this value. And it doesn't terminate, and it doesn't repeat any numbers as a decimal. So to see what how we can represent E is what happens to this expression. Here's our expression. Looks a little bit like what we just looked at a minute ago. But here, our interest rate is 100%. This is how I used to fool see, here's my interest rate right here, 100%, which is 1 instead of 10% or 25%. So I used to say to my students, what if I put $1 in the bank at 100% interest and I compound it once a year? They say, well, you have $2 at the end of the year. I say, okay, well, how about if I do it every single day? How about if I do it every quadrillionth of a second? Oh my God, they're writing down thousands of dollars. And so what happens to this number? What happens to this number as n approaches infinity? As n gets really, really big, what does this number approach? Well, thank God we have calculators. We can look at this really quick. So let's go up here and clear everything out. What's our expression? 1 plus 1 divided by n, which is x in this case, all raised to the x power. So I'm going to set my table. What's the first value I'm going to put in? 10. So what does this look like? 1 plus 1 over 10 to the 10th power, which is 1.1 to the 10th power. So let's see what number that is. I'm going to go to my table and I'm going to start it at 10. I'm going to ask it for values. Okay, so let's go to our table and I'm going to ask it for 10. So there it is, 2.5937. So 2.5937. So what this tells you is if you put $1 in the bank and you compound it 10 times, at the end of the year you'd have $259. They keep that $2.59. They keep this 37. What would this be? 37 10,000ths, right? They keep that. That's how they make their money over large numbers, right? They're not going to give you that. Anyway, never mind. All right, what about 100? What's this going to become? Okay, so $1 became $2.59. Let's go to 100. Let's make x 100. $2.70. Ooh, baby. I'm really making the bucks here. Plus. I want to clear these out here. I don't know how to clear the table out when I'm in the ask mode. All right, 1,000. Let's see what 1,000 is. 271.69. Picked up a little bit of money. 1 cent and a little more. All right. What about 10,000 times? Let's see what we get. 2.7183. And remember, they've rounded this. This is rounded. It's actually another 2 after that, and it keeps going. It's been rounded to 3. So it really wouldn't matter now what we put in here. If I put in this large number here, which is every second, let's see what we get. Same exact answer, 2.7183. So even if I did it every single second, which was 31,500 and whatever it was, 36,000 or whatever, I'd still get the same thing, because this expression, as n gets really big, never grows beyond e. And e is approximately 2.7128 if we take it out 4 decimal places. If you ever wanted to find the value for e, it's right here on your calculator. See this little thing, e to the x? So if you hit second e to the x, oops, let's clear. Let's get out of here. Second e to the x, and you want to know the value of e, then your exponent would be 1. So that would give you the value of e. And there it is out a few places. Okay. So the reason that when we compound every fraction of a second, we make those intervals infinitely small, we never grow beyond a certain point, is because of this number e. So when we put money in the bank, we can compound it over, several discrete intervals every year. And sometimes we can compound it continuously. That's what we mean when it's being done every fraction of a second. Yep. Yes? 8.2. Thank you. Thank you. 8.2? Okay. Yeah, 8.2 or 8.3, if I round it off. Thank you. Okay, so let's come back here now. The irrational number e appears as the base of it's a base for an exponential function. We call it the natural exponential function. You might say, it doesn't feel very natural to me. Well, it's actually used as a model for lots of things that deal with growth. Population growth, it could be population growth, it could be growths of animals in the wild if we reintroduce, say, like the gray wolf back in the Yellowstone. E is used as a base in lots of situations. If you ever remember the bell curve, grading on a bell curve, that function has e as a base. It doesn't have this form, it's actually much more complicated, but e is one of the bases in part of that formula. Okay, so here's the graph of 1 e to the x. And notice it goes through 0, 1, just like all of other parent exponential functions. And at 1, what would be the value right here? 1 what? What would be the exact value at 1? E, right, the base. Okay, and e to the x has to be between 2 to the x and 3 to the x, because its value, if we round it off, is 2.7. So if you take a quick look at GeoGebra, I'm just going to close this for a second. Close everything. Close everything. Here's GeoGebra. Okay, if we take a quick look at GeoGebra, let's squish this down a little bit. We want to see 1. We want to see it all go through 1. So here is 2 to the x in GeoGebra. Let's graph that. Oh, I forgot an equals. It always helps to have an equal sign, doesn't it? Yeah, equals. All right. Here's 2 to the x. Goes right through 0, 1. Acts like we know it. 2, 1, 2, 2, 4, 3, 8. And 3 to the x, let's call that g of x. And there's 3 to the x. Notice it rises much quicker after b is for any x value bigger than 0. It's getting bigger much more rapidly. So e to the x, so this has a base of 3, this has a base of 2. E is the number 2.78. So it must be between these two curves. And in fact, which curve should it be closer to? 3 to the x. And there you go. There's e to the x. So it acts just like a parent function, and therefore you can transform it, and just like we did with 2 to the x and 3 to the x. So let's take a look at an application problem involving compound interest. So here would be the 2 formulas you could use. If you're compounding it n times a year, then you use this formula. A equals P times 1 plus R over N, which we practiced doing, to the NT. Now, we didn't have T in our problem before because T was equal to 1. We weren't doing it multiple years. But this would be if you were doing it for multiple years, you would have some value for T other than 1. Now, compounding it continuously, this whole thing in here gets replaced with the letter E. So it's the principal times e to the RT. And does anybody know a quick way to remember this formula? P, Pert, right, that shampoo, right? So yeah, Pert, there's a shampoo called Pert. So that's how you, I don't know if it's still around, but people seem to remember it. All right, so I want you to use, I'd like tables 1 and 2 to do the problem, this first problem where you're investing $5,000 for 10 years at 6.5% compounded monthly. So tables 1 and 2, do that problem, check with each other and give me your answer. And the rest of the class, I want you to do the same problem, but you're going to compound it continuously. So check with each other. If you all agree, then let me know and we'll stop the clock, so to speak. Okay, so this is looking pretty good for tables 3 through 5, $9,577.70. Tables 1 and 2 are still having difficulty? Or did you come up with something? I'm looking right at you. 5,000, so you think it's $4,000 less? Let's take a look. A equals $5,000 is the principal. 1 plus our interest rate is 6.5%, which means R is 0.065. Monthly is 12. So we have 12 times 10 years, 120. So we put into our calculator 5,000 times 1 plus 0.065 over 12 raised to the 120th power. So let's see what that is. Whoa, I don't want you to be that big. So where's your error, Dan? What'd you do when I heard you say? Oh, you didn't do 12 times 10? Okay. All right, so let's see. We got 5,000 times 1 plus 0.065 divided by 12. And that whole thing raised to the 120th power. $9,560.92 approximately. So again, you can see that there is some advantage to doing it continuously. You earned about $16.22 more. Okay. So what you have for the remaining of the class is the first thing I'd like you to do is I'd like you to do the matching. Where's the matching? I would like you to do number 14, match these. The parent function here is e to the x. Match these transformations to the graphs below. There's 4 of them. And then I'd like you to continue with name that exponential function activity. There's 3 pages, so you have plenty to keep you busy. So before you get here, let me check everybody. I'd like to check this before you go on. So you have 20 minutes to work on this. Should give you lots of time.